Okay, so we are going to continue with a little bit of exponential function work here. Today we're going to start talking about e, and we're going to do a little activity as we're going. If you've never heard of e before, it's an irrational number like pi, and so we're going to talk about how we get that and where it comes from. If you've ever had a science course, then you've probably seen e before. But we're going to look at what happens when we invest $1 at 100% interest for 1 year at different compounding rates. Now, I know that it's unrealistic that somebody's going to pay us 100% interest, but I guess it's only on $1, so we're going to go with it, okay? So we have our compound interest formula here, which we learned last time. The A of t equals p times 1 plus r over n to the nt, right, with everything being, so p is my initial value, r is the rate expressed as a decimal, n is the number of times it's compounded, and t is our rate, or is our amount of time in years. Unless, well, we'll get to that in a minute. Okay, so I'm going to put in everything that I know. So I know we're going to invest $1, so that means that p will be 1. I also know that I'm 1 year, so t will also be 1. And then I know my rate is 100%, right? So that means as a decimal, if I take 100, and I really can think of it as dividing by 100, I get 1, right? Also, I can think of it as moving the decimal place back 2 places, and I get 1. So I'm going to put in 1 for p, 1 for r, and 1 for t. And when I do, that looks like this, okay? All right, now I really don't need these ones here and here, right? So n times 1 up here, so I'm just going to rewrite it without the ones, and I'm left with A of t equals 1 plus 1 over n to the n, okay? Now I want us to look at values. So n is the number of times it's compounding, and I do have it on Desmos here, so let's take a look at my Desmos. And so I kind of want us to look at these values. Let me see if I can get a good... Okay, so remember, now I know that my formula here is an x, but I'm in Desmos, so bear with me. So x in this particular case is the number of times it's compounded. So if I'm only compounding 1 time over here, then I'm going to make $2, right, after the year. If it's compounded semi-annually, then 2 times a year it's compounded. That earns me an extra quarter. So not bad, I'll take the quarter. So then when I go up to 4 times a year, compounded quarterly, right, then I will earn $2.44 if I round up to the dollar. And if I compound monthly, I jumped up to $2.61. Now, not giant jumps, right? Not terribly giant jumps. I'm only really making 20 more cents, and that's kind of an exaggeration there. So then I'm going to have it compounded every single day, 365. And now I'm up to 2.7145, and if I jump up, so daily is 365, and I thought, let's go crazy, let's do hourly, and hourly is 8,760 times per year, and so that gives us 2.718. Now you notice that that's a really big jump between 365 and 8760, right? But yet my decimal place, like, I still have 2.71 here. Now this second one, it would actually round up to 2.72 when I look at the third decimal, but really these are matching to 2 decimal places. And then if I really go crazy and I say per second, then I have 52,600. Then now I'm matching this one above it to 3 decimal places. It's 2.718. So I went from a really, 8,760 to 525,000, and I really only went up like 1/1000th of a, I went from 2.7181 here to 2.7182 here. Well, technically it would be 3 if I rounded it up with the 7. But then when I go to this 3 million, you notice my y values seem to have basically stopped. Now they're going up a little tiny bit, but look, they just keep agreeing at more and more places. And so what that means is that I really kind of have a horizontal asymptote here. I keep getting closer and closer to some weird number that's like 2.718 something, okay? And what that actually is what we call E, okay? So we say essentially that the limit as x goes to infinity, right, because we were looking at larger and larger and larger x values, right, this is our calculus words, as x goes to infinity, then this function here we say is equal to e. This is the definition of e. It's the limit as x goes to infinity of 1 plus 1 over n to the n. And we say that e to approximately 6 decimals is approximately 2.718282. Now when we were doing that, essentially, I mean, we were compounding it every second. So when we use e, we say that it's compounded continuously. Okay, so that's kind of where it comes from. So when you're looking at compound interest or things that are decaying in a compound way as well, then anything that is continuously doing that, we use this formula for e. Okay, and we have a new growth formula here. Okay, and it is a of t. Let's see, let me get it on the screen here. A of t is equal to, I call it PERT for short. It's P e to the RT. Okay, so now just like the other one, I'm going to bring it into that we used before. Okay, very similar things are happening. Okay, so the other formula here is A of t equals, this is the one that we started this with, 1 plus r over n to the nt. Now just like this formula, a lot of these, they mean the same thing. P is the same P here, it's the initial value. R is, in both cases, the rate expressed as a decimal, and T is typically in years unless it's explicitly stated otherwise. Okay, we assume it's in years unless it's explicitly stated and then we don't have any need for n in here because e takes care of the compounding because it's the continuous piece, and then A of t is the future value, right? We put in our current thing and the rate and the time, and it'll spit us out what it'll be in the future. All right, so we had an example where we did this before, and if we looked back at that other one, so it was compounded, I think monthly is what we did, and so I think when we did that we ended up with a value of like $7,454.16 when we compounded it like monthly. So we're going to use the same stuff here, the 5,000, 4%, but this time compounded, really this should say continuously, not I guess continually means the same thing, for 10 years. Okay, so instead of using our formula that looks like this, because we have this word continuous in there, we're going to use this one instead. So again, the 5,000 is my P, 0.04, right, the 4% as a decimal is the R, and then the T is 10. So we put it in our calculator like this, okay, remembering that if I'm like 0.04 times 10 is just 0.4, so if I put in my calculator 5,000 e to the 0.4, it'll spit me out this amount, right, $7,454.12. Now that's up about $5-ish, right, from this one that we did monthly. So not a big amount, but if we had depending on how much we initially invest and how long it's in there, it can make a big difference. But make sure that you put your parentheses around your multiplication here. If it's not multiplication, then it doesn't need the parentheses, but if there's multiplication in here that you want your calculator to do because you don't want to put in an extra step of calculating it before, then make sure you put the parentheses around it. Okay. Alright, so I thought we would do one more example. This one, let's see, that's not it. Sorry. Okay, so we're going to look at this one here. Okay, so this one we have a continuous decay this time. So we have radon 222, which is decaying continuously at a rate of 17.3% per day, and we want to know how much will 200 milligrams decay to in 5 days. Okay, so again we're going to use our PERT formula, because it does say that it's decaying continuously. Now remember when we were doing exponential decays before, now we had y equals 1/2 to the x, and that was an exponential decay, but most of the time we see exponential decays, then they're written like this, with the negative exponent here. And so usually we see the negative exponent with the decay, and that's what we're going to have here. So when it says it's decaying continuously, then our rate we should put in as negative 17.3%. Okay? So in this particular case here, we're going to use our formula again. So we have 200 milligrams is our initial amount, so that's our p-value here. And then 17.3%, and this is per day, so this time we're going to specifically say that t is in days because it's decaying continuously per day. So if it was continuously per year, then we would use t as in years, or if it was t as per month, then we would use t as months, but it explicitly says per day here. And so our t is in days, so that means in this case our t will be 5 here, and then 17.3 as a percentage is 0.173 as a decimal. Right, I'm dividing 17.3 by 100, which slides that decimal point 2 places to the left. So when I put it all in here, it looks like this. I put the whole thing in my calculator in one smooth motion, and I ended up with 84.21 milligrams. Do make sure that you can put these in your calculator and get out the right answer. I mean, the majority of it is setting it up right, but you're still going to lose something if you can't get these answers. Okay. So again, just want to reiterate that the important thing here is we found out that the limit as n goes to infinity of 1 plus 1 over n to the n is equal to e, and this is our definition of e. And it's really important to us, and we use it when things are growing or decaying at a continuous rate. Okay, so we always use the PERT formula when we have continuous growth or decay.